Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly Testing Tactics webinar series. Today's topic is Fundamentals of Partial Discharge Measurements. My name is Charles Nybeck, and I'll be your presenter today. I am a Substation Applications Engineer for Megger here. And we're going to start today with a presentation outline. First, we will go into an installation overview, followed by an introduction to partial discharge. Then we'll move into the conventional testing method, followed by the unconventional testing methods, and then we'll end with a brief product glance. So starting with a installation overview. When we talk about insulation, we primarily talk about three types of insulation. One being thermal, another being electrical, and the other being sound. Obviously today we're going to focus on the electrical side of insulations, often referred to as an insulator. So when we talk about insulators and conductors, what really differentiates the two? Starting with conductors, conductors have loose electrons. These loose electrons are attached enough to stay in position, but it doesn't take very much energy to knock them out of place. Metals are a prime example that readily lose and gain electrons and therefore rule in the list of conductors. When we talk about insulators, we more mean organic molecules which share electrons and that are held together in place that kind of restrict the flow of electricity. When we talk about insulators, you often hear the word dielectric. So what do we mean when we say dielectric? Dielectric are these materials that do not allow electricity to flow them. However, in the presence of an electrical field, the materials become polarized. And a prime example of this is a capacitor, where you have two oppositely charged plates, one positive and one negative, with an applied electric field. And you can see the polarization of the dielectric material that separates them, but restricting the flow of electricity. So when we talk about insulation materials, we typically talk about, there are a number of different high voltage insulating materials that can be used for certain applications. Here we have a list of common high voltage insulating materials, starting with gases. And that can range anywhere from air, which is 78% nitrogen, and that's very important when we talk about partial discharge, and we'll discuss this importance a little bit later. This also includes SF6, C5PFK gas mixture, and it includes liquids such as mineral oil, silicon oil, ester-based oil, and bio-based oil, and then ultimately solids such as ceramic, glass, mica, high polymer plastics, and resins. And the takeaway from this is that each material has its own permittivity and dielectric strength, making some of these materials more susceptible to PD activity, as well as the different properties of these materials causing different characteristics of partial discharge themselves. So when we talk about insulation, our main worry or our main concern with insulation is insulation failure. And there are three typical aging mechanisms when it comes to high voltage insulation, and that is thermal stress, mechanical stress, and electrical stress. And although electrical breakdown is the final failure mode of electrical insulation, electrical stress is not necessarily the dominating aging factor. It's rather believed that the aging mechanism is dominated by thermal degradation, and mechanical stress is caused by vibration and switching pulses. The National Fire Protection Agency states that the insulation breakdown is the #1 cause for electrical failure. This particularly means a lot in terms of partial discharge, because when it comes to medium and high voltage equipment, partial discharge or PD activity is one of the first indications of deteriorating insulation. And this is commonly seen in solid insulation with the phenomenon of electrical treeing, which is a damaging process due to partial discharges, progresses through a stressed dielectric insulation. So for instance, here you can see where it would have started and stressed and treed through the dielectric or the solid dielectric or insulation. And if it were to go completely through bridging both sides and cause ultimate failure, you could see a catastrophic event such as this blown out winding down here. And when we talk about people that are affected by insulation failures, really this kind of affects everybody across the board. I mean, and it could range from industrial, such as large manufacturing and cogeneration, to commercial, such as research parks and high rises, institutional campuses and hospitals, governmental agencies like military bases and large office complexes, as well as utilities, whether they be investor-owned or municipalities. So moving from the insulation overview into a introduction to partial discharge. So what is partial discharge? According to the IEC 6270 standard, partial discharge is a localized electrical discharge that only partially bridges the insulation between conductors and which can or cannot occur adjacent to a conductor. And it goes on to say that partial discharges are in general a consequence of local electrical stress concentrations in the insulation or on the surface of the insulation. And generally, such discharges appear as pulses having a duration much less than 1 microsecond. And as is stated, PD activity is present when the voltage stress across a void or an insulating material exceeds that dielectric strength of the insulating material. And when partial discharge activity takes place, many different physical and chemical changes may happen, which produce emissions that allow us to detect the partial discharge activity. And this can come in the form of dielectric losses, electromagnetic transient, pressure waves, sound, light, heat, and even chemical reactions. And some of these chemical reactions can produce, or some of this partial discharge can produce ozone. And this is particularly an issue in encapsulated environments where that can get to a real corrosive atmosphere. When we discuss partial discharge, there's many different ways that PD activity can manifest itself. Here we have 3 primary examples, the first being void discharge. So if we take a look at this leftmost figure, you see the solid insulation that has a void in it. Well, the solid insulation has its own dielectric strength, while the void that's filled with air has a separate dielectric strength. It's typically going to be lower than the insulating material around it. So when you apply your electric field, the electric field in that void may exceed that dielectric strength, where it may not have exceeded the dielectric strength in the solid insulating material here. And this will cause that void stress to grow, and then ultimately could cause breakdown between the 2 electrodes. Next, we have in the middle here, we have a example of surface discharge, where your high voltage is touching the surface of your insulating material, and due to contaminants or just a high electric field concentration, you have arcing activity between the surface of the insulating material and the high voltage potential. And this can cause PD activity on the surface here, or otherwise known as surface discharging. Here we have, on the right, we have an example of corona discharge, where your high voltage is not necessarily touching your ground electrode or your insulating material, but the insulating medium between, the dielectric strength has been exceeded, and therefore breakdown is occurring between those 2 potential levels. So moving into some properties of insulating materials. Here we have a list of typical breakdown strength of different insulating materials. The first one's air, which we had previously discussed briefly. And air is 78% nitrogen, which I mentioned earlier. And nitrogen is an electropositive gas, which makes it a poor insulator due to its availability of free electrons. But other gases, such as hydrogen or SF6, can be really good insulators when used in the compressed forms, such as GIS or GIL. For instance, the breakdown strength of SF6 at 4 bar is roughly 3 times higher than at 1 bar. And these gases or this medium, as I mentioned when we were talking initially about the different insulating materials, cause different characteristics of PD activity. So the rise time in nitrogen, which is an electropositive gas, is much slower than that of SF6 or C5PFK, which results in a more narrow measuring bandwidth, whereas SF6, which is an electronegative gas, would have a larger bandwidth. And here we have Paschen's law, which directly relates the breakdown voltage to pressure times distance. And here we have an example of multiple different Paschen curves where on the y-axis we have breakdown voltage, and then on the x-axis here we have pressure times distance. And you can see how the voltage varies based on the pressure times the distance. So moving into the occurrence of partial discharge. For the occurrence of partial discharge, 2 conditions must be met. First, the local electric field must have reached the critical inception field, meaning that the local electric field should surpass the electric field that is necessary for partial discharge to take place, or otherwise exceed that dielectric strength. And the second condition is the availability of a free electron to start the discharge avalanche. And this discharge avalanche is referred to as the Townsend discharge or Townsend avalanche, which is a gas ionization process where free electrons are accelerated by applied electric field, and they collide with gas molecules and consequently free additional electrons, as you can see. And these electrons in turn accelerate and free additional electrons. And this results in the avalanche multiplication that permits the electrical conduction through a gas medium. And there's 2 main processes to derive this initial electron. One is the ionization by photons, which is a natural event. And these photons would hit a gas molecule, knocking an electron to become available, or field emissions triggered artificially, such as X-ray treatment. And these statistical properties of these processes control the appearance of the PD pattern, and we will see an example of this later. So when we talk about starting electrons, there's provisions for starting electrons that change depending on the material. But one thing is certain. In all cases, free electrons are required to start partial discharge. So if there are no electrons, there is no partial discharge activity. As previously mentioned, when we were talking about conductors and insulators, we mentioned the fact that metal is a very good conductor because it readily gains and loses electrons. So there's plenty of free electrons on metallic surfaces, which means that immediate inception of partial discharge occurs if that local electric field exceeds that critical electric field. But when we talk about polymeric low energy surfaces, they literally offer no free electrons, so ionization is needed. And we talked about ionization through the photons hitting a gas molecule. These sources of the ambient radioactivity can cause, statistically speaking, cause roughly 2 times 10 to the 6th free electrons per second in a cubic meter. This results in delayed inception. So if not triggered artificially, statistically speaking, it takes on average 15 minutes until a spherical void of 1 millimeter in diameter is hit, and therefore discharge starts. And this is an issue when we talk about common test times of epoxy molded equipment, which is often too short. So it's recommended that longer test periods, at least 15 minutes or greater on epoxy molded equipment, is taking place to overcome the problems that would be overlooked or missed due to these internal defects having not quite taken place yet. So for one instance, a dry time transformer testing period is 3 minutes, which is only 1/5 of that 15 minutes, the statistical 15 minutes that it would take for the spherical void of 1 millimeter to start discharge. And here we have discharges in a spherical gas inclusion. And in this particular case, we're talking about having the high availability of a starting electron. So with the high availability of a starting electron, there would always be an electron available once the critical field is met. So the partial discharge occurs when the critical field is reached. Then discharge, the internal field breaks down to the residual field, and then it would charge again, and then discharge again to the, once the critical field is reached. And this causes a consecutive row of even pulses, and then the changing of the opposite polarity, and then again, once the critical field is met, discharge occurs, and this causes a phase shift, and in this case, in the first and third quarters. And here you can see the phase resolved partial discharge pattern, or the PRPD pattern, that shows a regular partial discharge pattern for this stable low discharge amplitude. You can see a lower amplitude due to this charge and discharge from the critical field to the residual field. And this is uncommon to have such high availability of the initial electron as well as the stable magnitude, and really only applies whenever there's strong radiation by X-ray or UV light that provides sufficient enough energy to achieve such regular discharge. But here we have another example, and in this example we have low availability of starting electrons. In this case, there is no such external radiation, only the ionization process of the natural radioactivity. And here you can see a random discharge occurrence whenever the local field is greater than the critical field. Rather than the critical field being met and dropping down to the residual field, the critical field keeps increasing until breakdown occurs. And you can see the breakdown being much higher in magnitude. And in this case of low availability of free electrons, the electrons start the avalanche after that time lag that's derived from the natural radioactivity that causes this delay and causes and here we have the typical phase resolved partial discharge pattern for such a case where we have a higher amplitude and this lower availability of starting electrons. Moving on, we have partial discharges, causes and measurement techniques. There are many different ways that partial discharge can be caused, but they all come down to dielectric stress. And this can come in the form of non-homogeneous distribution of electric field, the presence of bubbles in solid and liquid insulation, punctual effects that localize dielectric stress on insulation, presence of moisture, cracks or water pockets, could be caused by presence of contaminants on the insulation surface, as we saw in the instance of surface discharging, or could be just by the voltage exceeding the dielectric strength of the insulating material. And when we talk about measurement techniques, the partial discharge current pulses occurring within the high voltage apparatus cannot be measured directly because the PD source is not accessible. So therefore, there are many different means of measuring PD activity. And they are broken into conventional and unconventional methods. And the conventional method is covered by the IEC 6270 standard that was mentioned previously, where the partial discharge as apparent charge is measured in picocoulombs. And then you have your unconventional methods, and that can range anywhere from electromagnetic detection to acoustic detection, optical detection, and even chemical detection. Here I have bolded the electromagnetic and acoustic detection because they are two of the more popular methods and will be discussed in this presentation. So when we talk about testing, testing for partial discharge can be done either online or offline. When partial discharge testing is done online or offline, we typically talk about the IEC 6270 method. And this is mostly important for laboratory and workshop setups. Because the apparatus is offline and the test is done offline, this does require a separate power supply to induce the PD activity. This can come in the source of resonant test systems, damped alternating voltage sources, very low frequency VLF sources, high pot, and step-up transformers. As stated in the offline, the device under test has to be taken out of service, which can affect operating conditions such as gas type, pressure, and humidity that may differ from the offline testing rather than online testing. But one of the things you gain is the noise sources other than the radiated noise can be eliminated. When we talk about online testing, this is typical for commissioning and testing on site. This typically correlates to the unconventional methods and allows for more frequent testing or monitoring of partial discharge activity. And online testing offers a major strength in the ability to trend measurements and make comparisons based on prior measurement. And unlike the offline testing, online testing permits examination of the device throughout all the factors of influence, such as power loading, temperature, and humidity that you may not get when performing offline testing. Moving from that, we'll go into start talking about the conventional test method. Here we just kind of have a visual overview of what was already stated. You have your insulation or your apparatus, high voltage being applied, your partial discharge activity that emits many different things we can measure, such as optical effects, pressure waves, electrical effects like dielectric losses or high frequency waves, chemical effects, and heat. But right now we're going to focus on the electrical method. And of the electrical method, we will focus on the IEC 6270 or the conventional measurement method. Okay, so when we talk about here, we have the conventional method overview, and here we have the measurement circuit, the typical measurement circuit for the conventional method covered under the IEC 6270, and some important terms. So apparent charge, you've heard a couple times now, is the charge which, if injected between the terminals of the test object, would give the same reading on the measurement instrument as the PD current pulse itself. Since you can't actually measure the PD current pulse, this gives you the apparent charge equivalent to that current pulse. Here we have the PD inception voltage, which is the voltage at which repetitive partial discharges are first observed in a test object, and consequently the PD extinction voltage, which is the voltage at which repetitive partial discharges cease to occur in a test object. And just covering the typical circuit for PD measurement under the conventional method, here we have our high voltage supply that's necessary since this is an offline test. We have our filter to filter out any noise from our high voltage source, our object under test, followed by a coupling capacitor to decouple any partial discharge activity. We have our measurement impedance and our coupling device, followed by the connecting cable, which ultimately leads to our measurement instrument that gives us our partial discharge magnitude or our phase resolved PD pattern that we'll discuss a little later. Covering the calibration procedure, the partial discharge measurements are relative. So a PD detector is calibrated with a charge source of known magnitude, where that magnitude is the step voltage and multiplied by the capacitance in series. And just kind of look at the circuit over here, you can see the circuit is much the same. You have your high voltage source, filter, object under test, coupling capacitor, measurement impedance and coupling device, your cable, and your measurement instrument. The only difference in this is the calibration procedure in which you place your calibrator in parallel to the circuit with the object under test, and you have your step voltage generator in series with the calibration capacitor that spoke of right here. In the chart, a charge pulse impulse is generated using a step voltage and injection capacitor. And the charge impulse capacitor is connected across that test object to simulate the equivalent discharge as stated here. So across the test object, you input a known charge, and that's what allows you to create the relation between the partial discharge activity seen once the calibrator is removed. The IEC 6270 does have calibrator requirements. As we stated, the calibrator is comprised of a generator producing a step voltage pulse of amplitude in series with a capacitor. And just kind of going over some of these parameters of the IEC 6270 characterizing unipolar step voltage. Your rise time must be less than or equal to 60 nanoseconds, which is that point TR here from this point to this point here. The time to steady state must be less than or equal to 200 nanoseconds, which is when this wave starts and hits steady state here. And then ultimately the step voltage duration must be greater than or equal to 5 microseconds, which is the full duration starting here to the end of the step voltage here. And each of these PD events causes a reading proportional to the calibration that's taken place to express in terms of picocoulombs that scale factor that is determined. And just a note, Power Diagnostics, which we recently acquired, is one of just a few calibration labs worldwide that is able to perform the calibration procedure according to the IEC 6270 standards. Here we have a couple of common partial discharge detector principles, starting with the instrument with the traditional analog super heterodyne principle that allows both narrow and wideband detection. This is predominantly seen in earlier PD detection instruments, where you have your PD signal input coming into first the input attenuator, followed by a mixer with the first local oscillator fed into the first intermediate, with the second mixer and a second local oscillator fed into the second intermediate, and then finally fed into the demodulator, and then the meter and the oscilloscope for visualization of the partial discharge activity. Next, we have an instrument with the active integration, where your partial discharge signal is fed into, again, the attenuator, then fed to an amplifier, an integrator, and then the peak detector and evaluation unit here, and then ultimately, again, the meter and oscilloscope. And with this design here, the evaluation unit has the task to ensure that the behavior is according to the weighting curve of the IEC 6270 standard. Here we have the instrument with an early A to D or analog to digital conversion with post-digital processing. Here, again, your partial discharge pulse is fed into an attenuator that is fed to an analog digital converter, passed through a digital bandpass filter, then through a numeric integrator, and then your voltage source, your AC voltage source signal, has an analog to digital converter, then your digital post-processing through your acquisition unit, and then finally your evaluation and visualization unit. And this follows the idea of the 6270 so-called quasi-integration, but instead of using a low-pass filter, F2 on the filter block here, 3, takes care of the integration. So the numerical integration is sometimes not necessary. Here we have the instrument with the quasi-integration at a bandpass filter, and then the subsequent analog to digital conversion. So here, again, your PD pulse is fed into an attenuator, then an amplifier, passed through your bandpass filter, and now it's converted into a digital signal. Your AC voltage is converted into a digital signal, and then all of your digital post-processing in your acquisition unit takes place. And then again, your evaluation and visualization unit is last. And one thing that all the electrical methods have in common is that they use this bandpass filter to select the frequency bands which are necessary, and we'll see when in the standards, the current standards. Here we have visualization of PD activity, kind of the historic evolution of the visualization. First, we have an old partial discharge oscilloscope or partial discharge detection unit, which would give you an analog measurement. And finally, we had the oscilloscope measurement, followed by the Lissajous measurement or visualization measurement that made possible to bring out symmetry between the positive and negative cycles. Here in the middle, you have your count distribution. And then here on the right, you have your charge phase count. So you have your phase in the x-axis, charge in the y-axis, and then the count is actually the color of the PD activity. So if you were to look at a 3D version of this plot, you could see how high the counts are on the yellow activity as opposed to the decaying orange, red, and the gray. And that's what corresponds to the counts in this plot as well, as these are the same plot. You can kind of see the tails here. Sometimes you can kind of read a two-dimensional plot better with the third dimension being the color itself. So mentioning the standard that I talked about, I've mentioned plenty of times now. First, we're going to talk about the IEC 6270. This is a horizontal standard, which means it's a general standard for all testing, primarily described for laboratory and workshop testing. There are vertical standards that are application-based testing. And this standard, we have a detailed calibration procedure, which we covered earlier. The numerical integration method can be seen in Annex A3, while the step voltage response method can be seen in Annex A4. And you can see some figures of test circuits with their calibrators in figure A2. The standard has block diagrams of partial discharge measurement instrument principles, which we just described or just kind of covered. Annex F has non-electrical methods. The Annex H covers some test results with evaluation with direct voltage. And then the IEC 6270 has recommended frequency bands. And this is what we were talking about earlier when talking about all the electrical methods use this bandpass filter to choose their frequency bands. The wideband has a lower frequency limit of 30 kilohertz, or between 30 kilohertz and 100 kilohertz, while the upper frequency limit is less than or equal to 1 megahertz, with a total bandwidth of between 100 kilohertz and 900 kilohertz. The narrowband frequency range has a midband frequency between 50 kilohertz and 1 megahertz, with a full bandwidth between 9 kilohertz and 30 kilohertz. And again, these bands correspond to the partial discharge method of measurement as well as the medium of measurement. So again, going back to when we were talking about gases and the rise time of nitrogen versus SF6 affecting the frequency bandwidth that you'd measure. So that's where these recommended bandwidths come into play. Here we have the current IEEE standard, the standard IEEE standard 1434. This primarily covers rotating machines, but also covers the electrical and non-electrical methods of PD detection, such as electrical pulse sensing, RF radiation sensing, ozone detection, and acoustic detection. It does have a good cover of online versus offline testing, and also covers the coupling capacitor within Annex B, covering type tests and routine tests. There are some neat typical PD pulse phased or PRPD patterns that can be seen in Annex C, as well as typical time frequency classification maps seen in Annex D. So now that we've covered the conventional testing method, let's go ahead and move into the unconventional testing methods. First, we'll discuss the electromagnetic testing method, where PD detection is done by electromagnetic transients that are captured by means of inductive and capacitive sensors, as well as specially designed field probes. So when we talk about these sensors, the PD detection has different frequency ranges. And these can range from very high frequency, or high frequency rather, that has the range of 3 megahertz to 30 megahertz, to very high frequency, or VHF, that has a frequency range of 30 megahertz to 300 megahertz. That corresponds to wavelengths between 10 meters and 1 meter. And then the ultra high frequency range, which is the UHF range, that ranges from 300 megahertz to 3 gigahertz and corresponds to wavelengths between 1 meter and 1/10 of a meter. And for each asset, you have to test in the frequency range according to the test environment. So be wary of noise, outside noise, radioactivity, airports, things of that nature that may get in to your coupling devices. So when we talk about the field coupling devices for electromagnetic methods, there are two different types, inductive and capacitive. The inductive can include Rogowski coils with measurement frequencies ranging from 1 megahertz to 100 megahertz, or yoke coils ranging from 2 megahertz to 50 megahertz. And an example of an inductive field coupling device is this CT seen here. There are capacitive field coupling devices, such as film electrodes, that range between 1 megahertz and 50 megahertz, as well as antennas that come in the UHF range that cover both narrowband and wideband measurements, with narrowband being about 5 megahertz and wideband being up to about 2 gigahertz. And these are primarily seen on GIS. And here's some examples here where you have a flange sensor or window sensors that can be retrofit to GIS systems for PD measurements. When we talk about the unconventional methods, though, attenuation of the PD pulse is a real issue when using the UHF sensors. And attenuation is dependent on many different aspects, and that can be frequency, the geometry of the asset, reflection and refraction, the conductor material, as well as the mode of the PD transients themselves. And another big takeaway for the UHF method, or for the electromagnetic method, is that it cannot be calibrated. Instead, they have what is called a sensitivity check, and we will cover that in detail in the next couple slides. So here we have an example of two different types of UHF measurement devices. And the UHF signals can be detected in either the time domain or the frequency domain. The time domain can be characterized by the magnitude of the UHF pulse, where the frequency domain result is a spectra which shows the amplitudes of various frequency resonance simulated by the PD pulses themselves. And the UHF measurement, or the electromagnetic measurement, is ultimately recommended as the complementary measurement to the electrical or the IEC 6270 conventional method. And again, we were talking about wideband and narrowband. The UHF also measurement systems come in wideband and narrowband systems. Here we have an example of a wideband system, which is the recommended methodology, because you get to see the entire PD signal and not excluding any of the important signal features. And this happens by amplifying the broadband frequency spectrum and feeding it to a detector, which is sent to either a display or an analog digital conversion for display. Here we have a narrowband system, and you can see the difference where instead of looking at the entire PD signal, instead you're just looking at this small window. And here on narrowband systems, you run the risk of measuring in blind frequency spots. And the frequency spectrum often reveals important info about PD defect types, as well as their location. So running the risk of measuring in a blind frequency spot can really be detrimental to the overall measurement. And here we have the PD pulse magnitude. So this is where we go into the sensitivity check. So the sensitivity check has two steps. One is performed at the factory of the GIS manufacturer, where an artificial fault is created with a metallic span of a hopping particle, whose size is chosen to give a 5 picocoulomb peak signal. And in this, when doing this, they use the conventional decoupling methods of the IEC 6270 to be sure that they do indeed have this 5 picocoulomb peak signal and are able to get a PRPD pattern of this 5 picocoulomb signal. And the next step is to, while still at the manufacturer, is to inject a voltage signal between 5 and 50 volts into sensors nearby to find a signal strength that best fits the peak value of that 5 picocoulomb pattern. So for instance, you have an artificial pulse magnitude of 5 volts injected, and you can see where it lines up on the PRPD pattern, not quite at the peak. So if that's increased to 10 volts, you can now see that the injected signal aligns well with the peak of the 5 picocoulomb pattern seen here. So then the second part of the sensitivity check is done during commissioning of the GIS, where you would then, once commissioned, you would inject a signal into the sensitivity check value that you found, being this 10 volts, and the manufacturer on site, and then check the surrounding sensors, checking to see if the signal can be measured on the neighboring sensors without being overwhelmed by the noise floor. So first is to create a 5 picocoulomb defect, use the conventional decoupling methods to measure this, then inject a signal that corresponds to that 5 picocoulomb value, and then on the site inject that signal that was found during the sensitivity check at the manufacturer to be sure that the signal can be seen on site. And here's just an example of a 5 picocoulomb signal in the time domain. And again, be wary of noise. This noise can come from radio, TV stations, mobile transmitters, and nearby airports. Any high frequency noise. So the main takeaway is really this sensitivity check as a form of a correlation between a picocoulomb value and the decibel microvolt value that you get in the UHF measurement. Next, we have the acoustic measurement. And the acoustic emissions are caused by the PD events that cause mechanical vibrations. And this can be picked up using piezoelectric transducers, fiber optic acoustic sensors, accelerometers, condenser microphones, or sound resident sensors. And these PD pulses, their frequency spectrum is much above the audible sound band, and ranging anywhere from 10 kilohertz to 300 kilohertz. And similar to the electromagnetic method, attenuation of the PD pulses is a real issue when using the acoustic sensors. And again, it's based on many variables, such as the frequency, geometry, again, reflection, refraction, conductor material, physical boundaries. All of these can affect the attenuation of the acoustic signal. And again, this is kind of seen as a complementary measurement where the primary application is partial discharge location. That has a wide range of field applications, such as PD location within GIS, transformers, cables, and other assets. Here we have an example of two different types of sensors, one being structure-borne, which is actually applied to the structure, whether it be GIS or transformer, and the other being airborne, where you can use this in outdoor facilities and overhead lines to capture PD activity using sensitive microphones. And another big takeaway is similar to the electromagnetic method. The acoustic method cannot be calibrated as there is no correlation between the PD quantity apparent charge, because a calibration of acoustic method cannot be conducted to find a suitable reference value. But here we have an example of using the acoustic transmission method to locate PD. And when you use the acoustic method, it is necessary to have an electrical trigger. So the electrical trigger is necessary to conduct the acoustic measurement and is seen here in black with the 1. And you can see a time delay between the trigger signal and the acoustic signals that propagate thereafter. And the time delay can be used along with the acoustic wave velocities to determine distance. So for instance, here we have pressure wave velocities in oil and in steel, as well as a transverse wave velocity in steel. And these wave velocities can be used along with the time delay. So when you have meters per second and then the time delay in seconds, you can cancel that out and just get the meters. That gives you the idea of the location of the partial discharge activity. One thing to note here is that the sensor should be placed as close as possible to the PD source location, and this greatly improves the precision in locating the PD activity. So moving on, we got a brief glance at some of the products. Here we have the ICM system, which is our more advanced state-of-the-art partial discharge and tan delta measurement and analysis tool. It offers high-end signal pre and post processing, as well as the highest modularity and robustness available. It comes available with simultaneous real-time acquisition on up to 10 input channels and is capable of measurements under AC and DC. It does have integrated acoustic PD location functions, which we just covered, as well as integrated cable fault location features. And it's really seen as kind of the all-in-one measurement system. Next, we have the ICM Compact, which is a more popular detector for standard measurement tasks during daily work. It's has user-friendly setups. Again, offers high modularity and robustness. Frequency selective measurement for noisy environments. If you're trying to avoid some high-frequency noise, you can select your measurement frequency. Offers a multiplexer for multi-sample measurements, as well as integrated cable fault location feature, and even a radio interference voltage meter is optional, or RIV meter is optional in this with the ICM Compact. Next, we have the ICM Flex, which is a unique concept here, where the measurement system is capable of partial discharge, tan delta, power factor, capacitance, and power frequency measurements, where the acquisition is actually located on the high voltage potential, is capable of PD fault location with the DSO option, is capable of being used with multiple types of sources such as VLF, power frequency, or resonant frequency sources, is easy to set up and is user-friendly, is fully computer controlled, and is capable of Bluetooth or fiber optic communication for noisy environments. And finally, we have here the AIA Compact, which is a non-invasive PD detection and location for GIS and AIS, as well as cable terminations and transformers. The standalone detector that's fully operational by the push buttons you see here. No PC is necessary, and combines all of the non-conventional PD measurements such as acoustic, high frequency, and ultra-high frequency, so those electromagnetic and acoustic measurements that we covered in the unconventional methods in one instrument, and also boasts automatic sensor detection, so no matter the sensor that you plug in, the instrument would know and configure itself appropriately. So I'd like to thank everybody for their attention and participating in this presentation. Thank you all very much.